Chapter 3 of the ABC of Atoms. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The ABC of Atoms by Bertrand Russell. Electrons and Nuclei. An atom, as we saw in Chapter 1, consists, like the solar system, of a number of planets moving round a central body, the planets being called electrons, and the central body a nucleus. But the planets are not attached as firmly to the central body as they are in the solar system. Sometimes, under outside influences, a planet flies off, and either becomes attached to some other system or wanders about for a while as a free electron. Under certain circumstances, the path of a free electron can actually be photographed. So can the paths of helium nuclei that are momentarily destitute of attendant electrons. This is done by making them travel through water vapor, which enables each to collect a little cloud and so become large enough to be visible with a powerful microscope. These observations of individual electrons and helium nuclei are extraordinarily instructive. They travel most of their journey in nearly straight lines, but are liable to sudden deviations when they find themselves very near to the electrons or nuclei of atoms that stand in their way. Helium nuclei are much less easily deflected from the straight line than electrons, showing that they have much greater mass. By exposing these particles to electric and magnetic forces and observing the effect upon their motion, it is possible to calculate their velocity and their mass. By one means or another, it is possible to find out just as much about them as we can find out about larger bodies. An atom differs from the solar system by the fact that it is not gravitation that makes the electrons go round the nucleus, but electricity. As everybody knows, there are two kinds of electricity, positive and negative. These are mere names. The two kinds might just as well be called A and B. None of the ideas commonly associated with the words positive and negative must be allowed to intrude when we speak of positive and negative electricity. Each kind of electricity attracts its opposite and repels its own kind, like male and female. It is very easy to see electrical attraction in operation. For instance, take a piece of sealing wax and rub it for a while on your sleeve. You will find that it will pick up small bits of paper if it is held a little distance above them, just as a magnet will pick up a needle. The sealing wax attracts the bits of paper because it has become electrified by friction. In a similar way, the central nucleus of an atom, which consists of positive electricity, attracts the electrons, which consist of negative electricity. The law of attraction is the same as in the solar system. The nearer the nucleus and the electron are to each other, the greater is the attraction, and the attraction increases faster than the distance diminishes, and the attraction increases faster than the distance diminishes. At half the distance, there is 4 times the attraction. At a third of the distance, 9 times, at a quarter, 16 times, and so on. This is what is called the law of the inverse square. But whereas the planets of the solar system attract one another, the electrons in an atom, since they all have negative electricity, repel one another, again according to the law of inverse square. Some readers may expect me at this stage to tell them what electricity really is. The fact is that I have already said what it is. It is not a thing, like St. Paul's Cathedral. It is a way in which things behave. When we have told how things behave when they are electrified, and under what circumstances they are electrified, we have told all there is to tell. When we are speaking of large bodies, there are 3 states possible. They may be more or less positively electrified, or more or less negatively electrified, or neutral. Ordinary bodies at ordinary times are neutral. But in a thunderstorm, the earth and the clouds have opposite kinds of electricity. Ordinary bodies are neutral because their small parts contain equal amounts of positive and negative electricity. The smallest parts, the electrons and nuclei, are never neutral, the electrons always having negative electricity and the nuclei always having positive electricity. That means simply that electrons repel electrons, nuclei repel nuclei, and nuclei attract electrons according to certain laws, that they behave in a certain way in a magnetic field, and so on. When we have enumerated these laws of behavior, there is nothing more to be said about electricity, unless we can discover further laws or simplify and unify the statement of the laws already known. When I say that an electron has a certain amount of negative electricity, I mean merely that it behaves in a certain way. Electricity is not like red paint, a substance which can be put onto the electron and taken off again. It is merely a convenient name for certain physical laws. All electrons, whatever kind of atom they may belong to, and also if they are not attached to any atom, are exactly alike, so far at least as the most delicate tests can discover. Any two electrons have exactly the same amount of negative electricity, the smallest amount that can exist. They all have the same mass. This is not the mass directly obtained from measurement. Because an electron is moving very fast, its measured mass increases. This is true not only of electrons, but of all bodies, for reasons explained by the theory of relativity, which will concern us at a later stage. But with ordinary bodies, the effect is inappreciable, because they all move very much slower than light. Electrons, on the contrary, have been sometimes observed to move with velocities not much less than that of light. They can even reach 99% of the velocity of light. At this speed, the increase of measured mass is very great, but when we introduce the correction demanded by the theory of relativity, it is found that the mass of any two electrons is the same. Electrons also all have the same size, insofar as they can be said to have a definite size. For reasons which will appear later, the notion of the size of an electron is not so definite as we should be inclined to think. They are the ultimate constituents of negative electricity, and one of the two kinds of ultimate constituents of matter. Nuclei, on the contrary, are different for different kinds of elements. We will begin with hydrogen, which is the simplest element. The nucleus of the hydrogen atom has an amount of positive electricity exactly equal to the amount of negative electricity on an electron. It has, however, a great deal more ordinary mass or weight. In fact, it is about 1,850 times as heavy as an electron, so that practically all the weight of the atom is due to the nucleus. When positive and negative electricity are present in equal amounts in a body, they neutralize each other from the point of view of the outside world, and the body appears as unelectrified. When a body appears as electrified, that is because there is a preponderance of one kind of electricity. The hydrogen atom, when it is unelectrified, consists simply of a hydrogen nucleus with one electron. If it loses its electron, it becomes positively electrified. Most kinds of atoms are capable of various degrees of positive electrification, but the hydrogen atom is only capable of one perfectly definite amount. This is part of the evidence for the view that it has only one electron in its neutral condition. If it had two in its neutral condition, the amount of positive electricity in the nucleus would have to be equal to the amount of negative electricity in two electrons, and the hydrogen atom would acquire a double charge of positive electricity by losing both its electrons. This sometimes happens with the helium atom and with the heavier atoms, but never with the hydrogen atom. Under normal conditions, when the hydrogen atom is unelectrified, the electron simply continues to go round and round the nucleus, just as the Earth continues to go round and round the Sun. The electron may move in any one of a certain set of orbits, some larger, some smaller, some circular, some elliptical. We shall consider these different orbits presently. But when the atom is undisturbed, it has a preference for the smallest of the circular orbits, in which, as we saw in Chapter 1, the distance between the nucleus and the electron is about 1/100 millionth of a centimeter. It goes round in this tiny orbit with very great rapidity. In fact, its velocity is about 134th of the velocity of light, which is 300,000 kilometers, about 180,000 miles a second. Thus, the electron manages to cover about 2,200 kilometers, or about 1,400 miles, in every second. To do this, it has to go round its tiny orbit about 7,000 million times in a millionth of a second. That is to say, in a millionth of a second, it has to live through about 7,000 million of its years. The modern man is supposed to have a passion for rapid motion, but nature far surpasses him in this respect. It is odd that, although the hydrogen nucleus is very much heavier than an electron, it is probably no larger. The dimensions of an electron are estimated at about 100,000th of the dimensions of its orbit. This, however, is not to be taken as a statement with a high degree of accuracy. It merely gives the sort of size that we are to think of. As for the nucleus, we know that in the case of hydrogen, it is probably about the same size as an electron, but we do not know this for certain. The hydrogen nucleus may be quite without structure, like an electron, but the nuclei of other elements have a structure and are probably built up out of hydrogen nuclei and electrons. As we pass up the periodic series of the elements, the positive charge of electricity in the nucleus increases by 1 unit with each step. Helium, the second element in the table, has exactly twice as much positive electricity in its nucleus as there is in the nucleus of hydrogen. Lithium, the third element, has 3 times as much. Oxygen, the eighth, has 8 times as much. Uranium, the 92nd, counting the gaps, has 92 times as much. Corresponding to this increase in the positive electricity of the nucleus, the atom in its unelectrified state has more electrons revolving round the nucleus. Helium has 2 electrons, lithium 3, and so on, until we come to uranium, like the Grand Turk, with 92 consorts revolving round him. In this way, the negative electricity of the electrons exactly balances the positive electricity of the nucleus, and the atom as a whole is electrically neutral. When by any means an atom is robbed of one of its electrons, it becomes positively electrified. If it is robbed of 2 electrons, it becomes doubly electrified and remains electrified until it has an opportunity of annexing from elsewhere as many electrons as it has lost. A body can be negatively electrified by containing free electrons. An atom may for a short time have more than its proper number of electrons, and thus become negatively electrified. But this is an unstable condition, except in chemical combinations. Nobody knows exactly how the electrons are arranged in other atoms than hydrogen. Even with helium, which has only 2 electrons, the mathematical problems are too difficult to be solved completely. And when we come to atoms that have a multitude of electrons, we are reduced largely to guesswork. But there is reason to think that the electrons are arranged more or less in rings, the inner rings being nearer to the nucleus than the outer ones. We know that the electrons must all revolve about the nucleus in orbits which are roughly circles or ellipses, but they will be perturbed from the circular or elliptic path by the repulsions of the other electrons. In the solar system, the attractions which the planets exercise upon each other are very minute compared to the attraction of the sun, so that each planet moves very nearly as if there were no other planets. But the electrical forces between 2 electrons are not very much less strong than the forces between electrons and nucleus at the same distance. In the case of helium, they are half as strong, with lithium a third as strong, and so on. This makes the perturbations much greater than they are in the solar system, and the mathematics correspondingly more difficult. Moreover, we cannot actually observe the orbits of the electrons as we can those of the planets. We can only infer them by calculations based upon data derived mainly from the spectrum of the element concerned, including the X-ray spectrum. We shall have more to say at a later stage about the nature of these rings, which cannot be as simple as was supposed at first. The first hypothesis was that the electrons were like the people in a merry-go-round, all going round in circles, some in a small circle near the center, others in a larger circle, others in a still larger one. But for various reasons the arrangement cannot be as simple as that. In spite of uncertainties of detail, however, it remains practically certain that there are successive rings of electrons, 1 ring in atoms belonging to the first period, 2 in the second period, 3 in the third, and so on. Each period begins with an alkali, which has only 1 electron in the outermost ring, and ends with an inert gas, which has as many electrons in the outermost ring as it can hold. It is impossible to get a ring to hold more than a certain number of electrons, though it has been suggested by Niels Bohr in an extremely ingenious speculation that a ring can hold more electrons when it has other rings outside it than when it is the outer ring. His theory accounts extraordinarily well for the peculiarities of the periodic table, and is therefore worth understanding, though it cannot yet be regarded as certainly true. The previous view was that each ring, when complete, held as many electrons as there are elements in the corresponding period. Thus the first period contains only 2 elements, hydrogen, and helium. Therefore, the innermost ring, which is completed in the helium atom, must contain 2 electrons. This remains true on Bohr's theory. The second period consists of 8 elements and is completed when we reach neon. The unelectrified atom of neon, therefore, will have 2 electrons in the inner ring and 8 in the outer. The third period again consists of 8 elements, ending with argon. Therefore, argon in its neutral state will have a third ring consisting of a further 8 electrons. So far, we have not reached the parts of the periodic table in which there are irregularities, and therefore Bohr accepts the current view, except for certain refinements which need not concern us at present. But in the fourth period, which consists of 18 elements, there are a number of elements which do not correspond to earlier ones in their chemical and spectroscopic properties. Bohr accounts for this by supposing that the new electrons are not all in the new outermost ring, but are some of them in the third ring, which is able to hold more when it has other electrons outside it. Thus, krypton, the inert gas which completes the fourth period, will still have only 8 electrons in its outer ring, but will have 18 in the third ring. Some elements in the fourth period differ from their immediate predecessors, not as regards the outer ring, but by having 1 more electron in the third ring. These are the elements that do not correspond accurately to any elements in the third period. Similarly, the fifth period, which again consists of 18 elements, will add its new electrons partly in the new fifth ring, partly in the fourth, ending with xenon, which will have 8 electrons in the fifth ring, 18 in the fourth, and the other rings as in krypton. In the sixth period, which has 32 elements, the new electrons are added partly in the sixth ring, partly in the fifth, and partly in the fourth. The rare earths are the elements which add new electrons in the fourth ring. Niton, the inert gas which ends the sixth period, will, according to Bohr's theory, have its first 3 rings the same as those of krypton and xenon, but its fourth ring will have 32 electrons, its fifth 18, its sixth 8. This theory has very interesting niceties, which, however, cannot be explained at our present stage. The chemical properties of an element depend almost entirely upon the outer ring of electrons, and that is why they are periodic. If we accept Bohr's theory, the outer ring, when it is completed, always has 8 electrons, except in hydrogen and helium. There is a tendency for atoms to combine so as to make up the full number of electrons in the outer ring. Thus, an alkali, which has 1 electron in the outer ring, will combine readily with an element which comes just before an inert gas, and so has 1 less electron in the outer ring than it can hold. An element which has 2 electrons in the outer ring will combine with an element next but 1 before an inert gas, and so on. 2 atoms of an alkali will combine with 1 atom of an element next but 1 before an inert gas. An inert gas, which has its outer ring already complete, will not combine with anything. End of chapter 3.